Good afternoon, AP Calculus students. So, Mr. Chen again. So, today I would like to talk about the continuation with the power series along with its derivative and integral. So, if the function of f of x equals the sum of a sub n times the quantity of x minus c to the power of n. Okay, so the function approximation using the Taylor polynomial, and then we end up with the power series. So, this one is actually written as a sub 1 times x minus c to the power of 1. Started with 0, a sub 0. So times x minus c to the power of 0, which is 1, right? So just a sub 0 for the first term. Plus a sub 1 times x minus c to the first power plus a sub 2 x minus c quantity to the power of 2 plus blah blah blah. So it has a radius of convergence of capital R radius, it's greater than 0. Then on the interval, well, we do know that center is C, so on the interval, so let's say that interval from, let's say C minus R to C plus R, the interval. So f is differentiable and therefore continuous. Okay, it is. And also, moreover, the derivative and antiderivative of the functions are as follow. So f prime of x. So derivative of a of 0, then that'd be 0. Derivative of a sub 1 times x minus c, it's just a sub 1. Because this one, well, it's x to the first power, basically. So basically that turns out to be 1. So just the coefficient. And then the other one is a sub 2 times 2, or 2 times a sub 2, x minus c, quantity to the power of 3. Well, it's just 1. Not integral, it's just a derivative. And then plus blah blah blah. And then all the way to this term, so which is what? A sub n times x minus c to the power of n minus 1. So basically this one can be written as sigma from n equals 0. Well, 0 doesn't count it, so you actually start off with a sub 1. So n equals 1, as what we just showed that here. So to infinity, and then a sub n times n x minus c to the power of n minus 1. And now what about the integral? So the integral from here, so then that'd be a sub 0 times x plus a sub 1. Integrate this one, then that'd be x minus c quantity square over 2. And then plus a sub 2 x minus c quantity to the power of 3 over 3. And then plus blah 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 all over a sub n times x minus c to the power of n plus 1 over n plus 1. Okay? So that means this one is written as sigma. Start out with n equals 0 because that's considered part of it. And so that would be a sub n times x minus c to the power of n plus 1 all over n plus 1. So this one is just the general definitions for the derivative and the integral for the summation of the power series. So the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. Okay? So the intervals of convergence, however, may differ as a result of the behavior at the endpoints. Okay? So yeah, definitely we have to check the endpoint for the radius of convergence. Okay, so now let's look at that. This one here, consider the functions. So power series, x to the power of n over n. So obviously that equals, so x to the power of 1, which is x over 1, plus x squared over 2, plus x to the power of 3 over 3, plus blah blah blah, all the way x to the power of n over n. So find the interval's convergence of the integral of f of x and derivative of f prime of x. So you may be wondering f prime of x, so that means this one is going to be written as 1 plus x squared. Okay, bring down the power. So 3 over 3, so that one is gone. Okay, so keep going. Plus blah blah blah. And then x to the power of n minus 1. Okay, so this one can be written as sigma. So starting with n equals, well, let's see. So starting with n equals 0 of x to the power of n. Because x to the power of 0, that's 1. That's what we got. X to the first power, that's x squared, so on and so forth. Okay? So find out the radius of convergence. So once we get this one, and the other thing that you want to do, it's about the ratio test. Okay, so let me just pull this out. So once we set up the sum for the integral, and then we want to do the ratio test. So basically just like what we did for the previous video. So once we set up that the a sub n, so we want to find out that a sub n plus 1. So a sub n here, so that's x to the power of n. A sub n plus 1, so x to the power of n plus 1. So using the ratio test right here. Okay, so let's see what that is. So n goes to infinity. So we got x to the power of n plus 1 over x to the power of n. So this one, you can use the ratio test or you can use the root test. The limit root test, either way, because that's to the power of n. So we got x, absolute value of x. So in order to have the series being converged, so that means the radius must be less than 1. So just like the geometric, the common ratio. So this one is just like a common ratio there. It must be less than 1. So the radius, it's 1. And then the intervals of the radius convergence, so this one, x is less than 1, while this one is being positive. Negative, then that'll be x is greater than negative 1. So this one is being bounded from negative 1 to 1. Now again, we need to verify the endpoint. So the way to verify the endpoint, we plug in a number back to the original series, the integral series, so which is this one here. So this one be negative 1 to the power of n. So this one, it just keep alternating, so alternating. So negative 1, well, that would be 1 plus negative 1. And then, what else? Plus 1 plus negative 1. So this one just keep alternating, so eventually it's going to be what? Converge. And then what about if we plug in 1 there? So plug in 1 there, so we do have, so this one is kind of like a geometric, infinite geometric, this one is a geometric series. Okay, so it's like 1 plus 1 plus 1 plus 1 plus 1. So it's non-stop. So this one diverge. So for the interval, so this one is only for open brace from negative 1 to 1. So for the radius of the interval convergence. Okay, so from negative 1 to 1. And it's for the integrals of the function. And now what about for its derivative? So derivative, so let's go back to that, the previous slide right here. So if that's the derivative, so we just want to take the derivative, so then that'd be 1. No, the one that we did there, that was the, hang on a second. The one that we did, that was the derivative. Never mind. Okay, sorry about that. So that was the derivative. But now let's do the one with the integral. So then the integral would be x squared over 2 plus x cubed over 6. And then plus x to the power 4 over 12. and then plus blah blah blah, x to the power n plus 1 over n times n plus 1. Okay, so that means sigma n equals 1 to infinity of x to the power of n plus 1 over n times n plus 1. So using that to put in for the ratio test, the one that we generate. Okay, so using this one. So this time is for the integrals of the function. Okay, so this one is the integrals of f of x. Okay, so set up that a sub n equals x to the power n plus 1 over n times n plus 1. And then a sub n plus 1, which is x to the power n plus 2 over n plus 1 times n plus 2. So limit n goes to infinity. This one you don't want to use the root test, okay? Because that involves with a lot of different n terms. So x to the power of n plus 2 all over n plus 1 times n plus 2, and then divided by a sub n. That means you multiply the reciprocal, so n plus 1 over x to the power of n plus 1. So things that we can cancel out here. So obviously that n plus 1, but let me just make sure that everything is correct here at this moment. Yeah, n plus 1 got canceled. And then this part right here, n plus 1, n plus 2 with the base x. So this one, that turns out to be just x to the first power. So what we found out here, it's considered absolute value. Well, make sure that we put in absolute value of x times n over n plus 2. This part, if you just separate it out using the L'Hopital's rule, this one is 1. So basically, it's just absolute value of x. In order to have a series to be convergent, so this one is considered less than 1. Okay? So absolute value of x is less than 1, so separate it out. So x is less than 1 for the positive. Negative, x is greater than negative 1. So again, it looks like it's being bounded from negative 1 to 1 again for the integral. So this time, again, plug in the number back to the original function because we need to verify the endpoint. Because sometimes part of it, or both of them, might be considered part of the convergence interval at the endpoint. So let's say x equals negative 1. So x equals negative 1, so we do have negative 1 quantity to the power of n plus 1 over n plus 1. Okay, so this one, infinity. And it's alternating. So the thing is that if you compare that with the telescoping series, because that n plus 1 is kind of like a telescoping series, so we can prove that this one is considered a convergent series. Well, but the thing is that this one is alternating, so let's see. Yeah, simply just use that alternating series test. So this one showing that it's actually convergent. Okay, so this one converge. Because that limit as n approaches infinity, this one turns out to be 0. And then using that the higher term, you'll see that the higher term will be considered smaller than this the original term. So converges by the alternating series test. Or you can say that by the telescoping series test. So that means this point is included. And what about f1? So if this one is f1, so let's say x is 1. So by using the telescoping series, so it's 1 to the power of n plus 1, that's just 1. So this one, obviously, it's considered convergent. Okay, because those terms, they got canceled out, okay, eventually. and just left with one of the constant. Okay, so since they both converges by the telescoping, series test, and then this one here. So basically the interval's convergent, so then that'd be -1 to 1. So this one is slightly different compared to the derivative. So derivative, well, actually I make an error here. So this one is -1 to 1, close parentheses. For this type of alternating series, I would say that it's also considered divergent, because that they all got canceled, but sometimes could be -1 and also could be 1, depends. Diverge. So it's going up and down, -1, 1, or 0. So they both diverges. So that means this one is just open parentheses for the derivative. Okay, so but for the integrals of the functions, it's actually in between -1 and 1, but also the endpoint. So basically this one, it shows the big difference. It's like a common interval, but the difference is about the endpoint. Okay, so for the integral, so that means the endpoint at that position there, it's also considered integratable. But for the endpoint, for the derivative, it's not considered differentiable. Okay, so now let's go back to this template, and so pretty much that's what we got here. Okay, so again, any questions that you have, any comments, so make sure that you just put into the comment YouTube channel comment bar, and then I try to reply that as soon as I can. Alright, thank you for watching all those videos today. See you next time.